Mba633 instructional video prepared by Professor Amit Tata, School of Management, George Mason University. In this segment, we'll work a problem to develop a confidence interval for the difference between two population proportions. So in Dallas, some fire trucks are painted yellow instead of red to heighten their visibility. During a test period, the fleet of red trucks made a certain number of runs and had 20 accidents. The yellow fleet made a certain number of runs too and had 4 accidents. So we are to develop a 99% confidence interval for PY minus PR. What do those letters represent? The subscript yellow represents the population of all yellow fire trucks, and the subscript R represents the population of all red fire trucks. PY is the probability of an accident for a yellow fire truck, and PR is the probability of an accident for a red fire truck, or the proportion of runs of yellow trucks that end up in accidents. PR is the proportion of runs for red fire trucks that end up in accidents. So I want to compute a 99% confidence interval for PY minus PR. So you remember the usual process of computing a confidence interval. A confidence interval simply consists of the corresponding sample statistic bracketed on either side by a margin of error. So let's look at the sample statistic. The sample proportion for yellow trucks is 4 accidents divided by 135,035 runs, which is approximately 3 times 10 to the minus 5. And the sample size, of course, is 135,035 runs. Similarly, for red trucks, the sample proportion is 20 accidents out of 153,348 runs, which ends up being 13 times 10 to the minus 5, and the sample size for red is 153,348 runs. So in order to compute a confidence interval for PY minus PR, the corresponding sample statistic that we use is the difference in the sample proportions, P bar Y minus P bar R, which ends up being minus 10 times 10 to the minus 5. So that's the sample statistic. And now I have to bracket this on both sides by the margin of error. So we know that if the samples are large enough, then the sample statistic P bar Y minus P bar R has a normal distribution. But are the samples large enough? The two tests that we have to do for each of the samples is n times p greater than or equal to 5, n times 1 minus p greater than or equal to 5. You can see that these two conditions are comfortably met for the red trucks. Okay, so n times p for the red trucks is 20, which is certainly more than 5, and n times 1 minus p is way more than 5, so it's comfortably met for the red trucks. But for the yellow trucks, n times p is actually 4, and n times 1 minus p is comfortably greater than 5. So it's marginal for the yellow trucks, but we'll still proceed on the assumption that those two conditions are met, and we have large sample conditions being met for both these two samples for the yellow trucks and the red trucks. Given that, so we will assume that it follows then that the sample statistic P bar Y minus P bar R has a normal distribution. What is the standard deviation of this normal distribution? The standard deviation of P bar Y minus P bar R is given by this expression. It's simply the standard deviation of the sample proportion for the one population case, and just written twice because we have two populations, one for yellow, one for red. We add up these two variances and then take their square root. And if you work out the math, if you plug in the value of P bar Y, P bar R, and the respective sample sizes for the yellow and red trucks, you will end up with 3.27 times 10 to the minus 5. And I hope I did my arithmetic correctly, but I have checked it, so that's what it turns out to be, 3.27 times 10 to the minus 5. That is what one standard deviation is. Okay. Of course, we need to know how large a margin of error do we need in standard deviations in order to be 99% sure. So same sort of logic, I want a lower limit and an upper limit, and the difference between the middle and the upper limit is the margin of error. This is the margin of error, just the width from the middle to the upper extreme, or from the middle to the lower extreme, is the margin of error. So I want this lower limit and the upper limit to be large enough such that this shaded area here is 99%. I want to be 99% sure. So the area under the sampling distribution between the lower limit and the upper limit of the confidence interval is 99%. So how large does u, the upper limit or the margin of error, have to be? So the built-in function that I need to use, of course, is norm S inverse, and the probability value that I put in is not 0.99 but 0.995, because that's the area of the yellow shaded portion plus the little tail to the left. Norm S inverse needs the area to the left of u. So this turns out to be 2.575. So my margin of error has to be 2.5 standard deviations, 2.575 standard deviations large, if I want to be 99% sure. And how much is one standard deviations? We just saw that it was 3.27 times 10 to the minus 5. So for our specific case over here, the margin of error is simply 2.575 multiplied by, let me wait for the screen to come back up, 3.277 times 10 to the minus 5. Okay, so let's see what that turns out to be. Is equal to 2.575 times 3.27 is 8.42. Okay, so my margin of error is equal to 8.42 times 10 to the minus 5. Okay, so I am 99% sure that Py minus Pr lies between minus 10 times 10 to the minus 5 minus 10 times 10 to the minus 5 plus or minus 8.42 times 10 to the minus 5. So that is my confidence interval. It's a sample statistic bracketed on two sides by the margin of error. I missed the decimal point here. 8.42 times 10 to the minus 5. So minus 10 times 10 to the minus 5 plus or minus 8.42 times 10 to the minus 5, or approximately 18.4 times 10 to the minus 5 to about 1.5 minus 1.5 times 10 to the minus 5. That's the confidence interval. So you have the lower limit and the upper limit. So this is how you go about computing the confidence interval for the difference between two population proportions. The logic is exactly the same as in the single population case. You first compute the sample statistic, then you figure out your margin of error based on how confident you want to be, and then you bracket the sample statistic on both sides by the margin of error. That's the basic procedure. The only complication here is because we have two populations, the expression for the standard deviation of the sample statistic is a little more complicated than in this single population case.